Weil from the University of Maryland, a soil scientist, my early collaborator with Steve Groff, whose farm I'm standing on right now. And one of the things I've been working on over the past decade or so are trying to innovate with cover crops to make them more attractive to farmers, and also to make them do more for both the farm and for the environment and for the bottom line. And we recently got a grant from the Northeast SARE, that's the Sustainable Agriculture and Research and Education program in the USDA, to look at what we are calling deep nitrogen. And this is basically trying to test the hypothesis, or our idea, that cover crops as they're commonly used, especially in Maryland where the state subsidizes cover crop use, we think that they're missing most of the nitrogen, which is a detriment both to the Chesapeake Bay, which receives that unwanted nitrogen, and to the farmer, who loses that expensive nitrogen. And we think the cover crops are missing it because the nitrogen is very deep, deeper than the usual 1 or 2 feet that farmers typically think about. We think it's probably 3 or 4 or 5 or 6 feet, maybe even deeper than that. And that if you don't catch this in fall, it'll be gone over the winter with all the wet weather, and then by the time cover crops start growing again in spring, before they're killed, it'll be too deep to catch. So that's the kind of hypothesis behind our project. And so in order to test this, one thing we're having to do, which is pretty difficult, but our team here has figured out ways to do it, is to get soil samples from about 7 feet deep. So we're getting these samples from different plots that were planted in cover crops last fall. We took samples early in the fall to see what was left over by the time the corn crops stopped taking up their nitrogen. This would be around late August, early September. There are hundreds of pounds of nitrogen, sometimes as much as 400 or 500 or 600 pounds of nitrogen per acre in the top 7 feet or so. So this represents a huge loss to the farmer. This is valuable nitrogen. It also represents a huge hazard to water quality, because eventually the deeper nitrogen there is going to get into the bay or get into the rivers, where it'll cause eutrophication. So the experiment we have here on the Groff farm is a variation of one that we have on about a dozen different farms in the region, where we have a control plot with no cover crop, which is in Pennsylvania still probably the most common thing to follow a crop in the winter. We have rye or triticale, a winter cereal, which is the most common type of cover crop in the region, and is certainly the standard in Maryland that the Maryland Department of Agriculture kind of judges other cover crops by. We have the tillage radish, which is Steve's brand of forage radish, and that's a very aggressive cover crop, which I've done a lot of work on, and we think it's very deep-rooted and gets roots very quickly, so we wanted to have that as a comparison. And then we are looking at a mixture, which is a three-way mixture. It's the radish, the cereal, in this case triticale, and the legume mixed in, and we want to see how that performs. In some places we're doing it at different planting dates. Here we did it at an early planting date. We think it's critical to get the cover crops in as early as possible so that they can perform in the fall, rather than wait for the little cover crops to survive the winter and perform in the spring. What we think happens is the cover crops pick up nitrogen from very deep, bring it up to the surface, and we hope that some of that nitrogen will be available for use by the next crop, and so we should be able to answer some of those questions. Here we're just measuring where you extract the nitrogen and find out what's soluble in water or in a salt solution, so it's pretty close to what's soluble in water. And this would be nitrogen that's moving down slowly through the profile, both the nitrate form, which moves quickly, and we find quite a bit of ammonia, which moves much more slowly, but we think it builds up over time, largely from manure application. And this farm gets pretty regular manure application, as do most of the farms in this particular part of Pennsylvania. So as that manure decays and releases ammonium nitrogen, this is the same kind of nitrogen that's in urea fertilizer and most fertilizers, it moves slowly down the profile because it is absorbed by the soil, by the cation exchange, but we think it moves down enough so that we're finding it all the way down to as deep as we're looking at 7 feet. We don't think it's moving through so fast, but there is a large storehouse of ammonia that would at least provide a one-time value if you could get a deep cover crop to clean it up. We did do some work with some nitrogen isotopes. There's a natural nitrogen, has an atomic number of 14, but there's also a naturally occurring but very rare isotope that has an atomic number of 15. So the atoms are heavier. It's not radioactive, it's not toxic, it's not, we're breathing it in all the time. There's a certain percentage in the air. But if we apply a fertilizer like potassium nitrate that has a very high percentage of this, actually we applied one that almost all the nitrogen in this potassium nitrate was N15, not N14, 99%. This is expensive stuff. Little thimbleful costs $100, but we placed this in the soil last fall at a couple of sites on a sandy soil and a clay soil. And we placed it at about 3 feet deep or a meter deep, and at 2 meters deep or almost 7 feet deep, and then planted the cover crops. And this way, when we harvest the cover crop, we can tell from the isotopic signature. Again, this is an expensive analysis. It doesn't use standard laboratory equipment, but it uses a mass spec which can separate out these two different kinds of nitrogen. And then we're looking to see if the percentage of that N15 is elevated, is higher than the background level. And sure enough, we were able to actually find that in the cover crops that were planted over the nitrogen that was placed at about 3.5 feet deep or 1 meter deep. By the time we sampled those cover crops, of course, it had moved down to about 135, 140 centimeters, so it was more like 4 or 4.5 feet deep. So we'd like to develop cover crop systems that can catch that nitrogen, bring it back, at least use some of it for the next crop, so the farmer can spend less on fertilizer and realize a benefit from that, and at the same time make sure that the groundwater is a lot cleaner.